Welcome back. What I'd like to do today is, I guess, talk about a couple of different things. So first I want to talk about some invariants arising from a hyperbolic structure. So that'll be probably about the first half of the talk. And then I wanted to talk a bit more about techniques for computing hyperbolic structures, this time particularly for three-dimensional orbifolds. Okay, so I guess there's a few references there, but maybe I'll come back to those later. So as we've seen already, we have this very powerful Mostow-Prasad rigidity theorem for hyperbolic manifolds of finite volume in dimension 3 and above. Do we have the pointer? The pointer somewhere? Okay, anyway, that's all right. So in particular, okay, thanks for that. Yeah, great. So if you have hyperbolic manifolds of dimension greater than or equal to 3, for instance, then if the fundamental groups are isomorphic as abstract groups, then in fact the manifolds are isometric. And there's a similar result for hyperbolic orbifolds in these dimensions. So one of the things this means is that any kind of invariants coming from the geometry are actually going to be topological invariants. So this gives a very sort of powerful technique for trying to classify, say, hyperbolic three manifolds. Okay, so sorts of things you might look at. One thing's the hyperbolic volume. So each hyperbolic manifold has a volume that you can look at. You could look at things like lengths of closed geodesics. These will also be topological invariants for your manifold. You can also look at sort of analytic invariants. So for instance, using the hyperbolic metric, there's a Laplacian defined in the manifold, and things like the eigenvalues of the Laplacian are also going to be interesting topological invariants. Okay. Another thing we get are arithmetic invariants or algebraic invariants, as I guess we've seen yesterday in Walter's talk. So just a quick reminder, some examples of this. If you write your hyperbolic manifold as a quotient of H3 divided by a discrete subgroup of PSL2C, then this rigidity says the group gamma is actually unique up to conjugation in PSL2C. So that allows you to find lots of algebraic invariants. For instance, there's a trace field, which is a field generated by traces, or if you like, plus or minus traces of all the elements. Because the trace is invariant under conjugation, so you get a well-defined trace for each element. You can also look at the invariant trace field. So here's another way to describe it. It's the field, the extension of the rationals generated by all the squares of traces. I guess you can show that that matches up with Walter's definition. Okay, and in fact, both of these things are algebraic number fields. The trace fields, not necessarily invariant under commensurability, but this invariant trace field is actually a commensurability invariant, as Walter mentioned yesterday. And then you can look at other things like the invariant quaternion algebra. That's another important sort of algebraic invariant. Okay. So I want to concentrate first on the volume. So the hyperbolic volume, I think it's perhaps the most important single invariant for a hyperbolic manifold. It gives a very good way of distinguishing lots of hyperbolic manifolds, and it's kind of the most natural way to measure the complexity of your hyperbolic manifold. I'll talk a bit about in tomorrow's lecture about how you can actually compute these volumes, but basically if your manifold is divided up into, say, ideal tetrahedra, there's actually nice formulas involving so-called Lobachevsky functions or dilogarithms to compute the volume of each tetrahedron, then you can add them up to find the volume of the whole manifold. So this is actually something that's very easy to compute. Now, it's not a perfect invariant in the sense you may have different manifolds with the same volume. However, there's only finitely many manifolds of any fixed volume. So up to sort of finite ambiguity, it is just about a complete invariant. Now, I wanted to start off with a couple of basic results. These go back to Thurston and also some of these to Jorgensen. So you could ask, what does a set of all volumes of hyperbolic 3 manifolds look like? It turns out it's actually a very interesting sort of picture. So if you think about H isometric classes of complete orientable finite volume hyperbolic 3 manifolds, then you have a natural function going from these hyperbolic manifolds to the reals where you take the volume. So it's got some very nice properties. First of all, it's finite to 1. So that's what I just mentioned, this finite number with a given volume. The image is actually a well-ordered subset of the reals. That means each non-empty subset has a smallest element. So in particular, there's some smallest volume for hyperbolic manifolds. It's also a closed subset, and it's got an interesting kind of structure. It's so-called order type omega to the omega. Now, the last thing, what that means is the following. So you can arrange the set of volumes as follows. So first of all, there's some smallest volume, V0, which is a positive number. So then you get some next volume, V1, next volume, V2. I probably should have had less than or equal to here. So some of these might actually coincide. So you go through all the integers here, and then you get an accumulation point. So you get a first kind of limit point, V omega. So it's a limit of all the volumes below this point. So then you go up, there's a next volume, V omega plus 1, then V omega plus 2. And eventually you get to another accumulation point, which is V2 omega. So maybe I should draw a picture here. So I kind of picture something like this. So here's V0, then we've got V1, V2, and then these accumulate at some first limit point like this. So that then you get a next volume. These all accumulate again at something like V2 omega. Then there's going to be another accumulation point, V3 omega. And these accumulation points start accumulating, and first accumulation point of those is something called V omega squared. And then this kind of pattern continues. So here you can think of all the volumes as indexed by polynomials in omega with integer coefficients. So this is a really beautiful picture of the set of volumes. This all continues. So I should like this. So this raises lots of sort of natural questions. So you can ask about what are the sort of smallest volumes for different kinds of manifolds. So V0 is going to be the smallest volume. V1's the next smallest. V omega is going to be the first limit volume. And that actually represents the volume of a cusped hyperbolic 3 manifold. So that corresponds to a cusped manifold. And each of these limit points actually corresponds to a volume of some cusp hyperbolic manifolds. And in fact, so here we have this kind of accumulation as you go to V omega. That actually arises from this process of hyperbolic downfilling. If you take a sequence of downfillings on this cusp manifold, you get a sequence of volumes approaching this limit. Now I'll come back and say a bit more about that later. So let's see, so what's known about some of these last volumes? Well, Chow and Meyerhoff proved that the first limit volume is about 2.09029. It's actually the volume of the figure 8 knot complement. So the example we looked at the other day gives you the smallest possible volume for these cusped manifolds. And there's another sort of closely related manifold with the same volume. Okay, so a very obvious question is, what is this lowest volume? And this was an open problem for many years. So I guess from the early work of Thurston and work of Jeff Weeks from, say, early 1980s, lots of volumes were computed. So lots of examples were known. And the lowest volume that was found was something like this, about 0.9427, which is it's a volume of a so-called Weeks manifold, which comes from Downfilling on the Whitehead link. So you do some kind of 5 minus 1, 5 2 surgery on the Whitehead link. That gives you a closed manifold with this volume. And I guess for a long time, one of the key problems was to show that this was really the lowest volume. And this has been proved very recently by the work of Gabay, Milley and Meyerhoff. So we now know we know now the lowest volume. So this is actually the simplest manifold in the sense of volumes. Okay. So let me say a little bit about this sort of Thurston-Jorgensen theorem, which gives you this kind of picture for the whole set of volumes. There's kind of two key ingredients. So one is the hyperbolic Dane-Surgery theorem. The other one is the following result. So it says if you fix some number, say v greater than 0, you can find a finite collection of, it's going to be cusped hyperbolic 3 manifolds, so that every 3 manifold of lower volume less than or equal to v comes from Dane-Surgery or Downfilling on one of this finite number of cusped manifolds. Okay. So this really comes by some kind of geometric limit argument. And yeah, so a bit of geometry analysing the sort of thick parts of hyperbolic manifolds. Okay, so I won't say anything more about that. But so this is a very nice kind of picture of the structure of all the hyperbolic 3 manifolds. And I guess what we'd like is to make this more explicit. Okay, you'd actually, if you're given some number v, you'd actually like to come up with an explicit collection of hyperbolic manifolds as in this theorem. And if you could do this, then you can start getting a nice classification of the lowest volume hyperbolic manifolds. Now, I guess, so there's been a big breakthrough here. I guess it's been going on, over the last maybe 5 or more years in the work of Gabay, Meyerhoff and Milley. So they've introduced some sort of new kind of structure, this kind of mum structures in hyperbolic manifolds, which really give a good picture of the low volume manifolds. Now, I won't say anything more about that. That would be kind of a whole series of separate talks. But here's the kind of thing that they can prove. So this is kind of a very explicit version of the previous general result. So if you have a 1 cusp hyperbolic manifold with volume less than 2.848, then in fact this can be obtained by Downfilling one of a finite list of 21 explicitly known hyperbolic manifolds. So this is kind of a very precise version of the previous result. This gives you a very nice picture for all the cusped hyperbolic manifolds up to this particular volume. And okay, so this requires a lot of work. It uses this kind of mum technology. It also uses sort of rigorous computations to estimate volumes. So one of the applications of this is the proof that this Weeks manifold is a unique closed orientable hyperbolic manifold of lowest volume. Turns out that the lowest volume manifold also has to come from downfilling on one of these one-cusp manifolds. So by analysing kind of downfillings on all these 21 manifolds, you can actually prove that this Weeks manifold has the lowest volume. And I just point out, as you might guess, this is actually an arithmetic manifold. Okay, and in fact, the first, I'm not sure. I mean, the first handful or more of lowest volume known manifolds are all arithmetic. So yeah, somehow being arithmetic helps you, you have this kind of extra symmetry which helps to give you low volumes. Okay. Now I'd like to say a little bit more about the downfilling process and how that leads to this kind of accumulation of volumes. So I guess yesterday I introduced this process of downfilling. I just want to make it a bit more precise today. So we'll start off, say, with a one-cusp hyperbolic manifold. So the figure 8 knot's a good example. Figure 8 knot complement. You can always, by using the Margulis lemma, you can see this always looks like the interior of a compact manifold with torus boundary. So we've got, say, M bar, it's compact, and the boundary T is a single torus. Now I'd like to parameterize the simple closed curves on this torus. So if we fix a basis for the fundamental group, that's just Z cross Z, then for each pair of integers, say with no common divisor, you get a nice corresponding simple closed curve on the torus defined up to isotopy. And I'm going to write MPQ for the corresponding downfilling. So what that means, so you take this manifold with boundary, you glue on a solid torus so that the PQ curve bounds a disk in this added solid torus. So that's PQ downfilling. Okay. Now, so when you do this process, so we had this kind of manifold with boundary, we add on this solid torus. So this, that goes to PQ curve on the torus, which is the boundary of M. Okay. Inside the solid torus, you have this sort of centre circle. And that's going to give you some geodesic, which I have called gamma PQ. So you have this kind of nice simple closed curve in the centre of the torus, and that's going to be homotopic to a geodesic, which I call the core circle. Okay. Now we can actually say a lot about how the geometry changes when you do downfilling. So this first result basically goes back to Thurston in his lecture notes, Princeton lecture notes. So the first part of the theorem, which I mentioned kind of already, says that this downfilling is hyperbolic whenever, say, the size of this surgery curve is sufficiently large. For instance, absolute value plus absolute value of P plus absolute value of Q is sufficiently large. So this says there's just a finite number of exceptions where the result is not hyperbolic. But now you can say a lot more about how this occurs. So in fact, if you look at the manifolds MPQ, they actually converge geometrically to the cusp manifold M. So this is in the same sense that Professor Ishiko was talking about. It's Gromov-Hausdorff convergence. So you imagine what happens is have these manifolds, the kind of core geodesic gets shorter and shorter. It moves further and further away from some fixed point in the manifold, and in the limit a cusp develops. So there's this kind of nice picture of geometric convergence to the cusp manifold. Now from this you can see that the volume actually converges to the volume for the limit manifold, and with some more work you see it actually converges from below. So that gives you this kind of picture. So you have a sequence of manifolds increase with volumes increasing to the volume of the cusp manifold as the limit. So that's how you get this kind of picture. The other thing you can see from this kind of geometric picture is that the length of the core geodesic goes to 0. Okay, so that's kind of the first version of this, how the geometry changes, going back to Thurston. Now, in fact, you can actually make this a lot more precise. So it's really understood very well how the geometry changes when you do downfilling. And I just want to mention, okay, so here's a more precise version of this. So we can actually estimate the change in the volume and the core geodesic length in terms of the kind of size of the surgery curve. So let's see. So here the setup again is the same as before. We've got a one cusp hyperbolic manifold. But yeah, so I want to measure the lengths of these curves using the geometry on the cusp. So how can we do this? Well, what we do is take a horospherical torus cusp cross-section. So remember in our figure 8 knot example, we could cut off the corners of the tetrahedra. We get a whole lot of little Euclidean triangles which are contained in horospheres. And in the complete case, they fit together to give you a Euclidean torus. So that's what we want to do. We want to take this kind of Euclidean structure on the torus coming from the hyperbolic structure. Now this thing, it's not well defined. It's only defined up to scaling. So if we go back, the picture of the cusp, okay, something like this. I've got this line. So here's a picture of a cusp. And there's lots of choices for T. So you could take one of these cross sections, or you could move it out, in and out, and you'll get Euclidean structure which just differ by scaling. So T is kind of well defined up to scaling. Okay. Now, what we're going to do is take a curve on this torus and measure its length. So if we take, what we can do is look at the length of the surgery curve by measuring the length of the corresponding Euclidean geodesic. So on this torus over here, we've got some curve that we're interested in. So maybe this is our okay, so that's gamma. We're going to do, this is our PQ curve. That's the thing that's going to bound a disk. So how do you measure its length? Well, you could take the Euclidean geodesic. So that'll have some length, say L of gamma. But that's not really well defined because we could have changed the cross-section and rescale everything. So there's a better thing to look at is the normalized length, which is the length in the Euclidean torus divided by the square root of the area. So that's actually independent of the choice of cross-section. And that's kind of a nice measure of how big the curve is in a geometric way. So if you do this, it turns out there's very nice formulas for the asymptotic behaviour of the length and the volume, which are due to Neumann and Zagier. So as the length of this surgery curve goes to infinity, so L hat's the normalised length, you can see the decrease in volume that's going from the cusp to the closed manifold. It's asymptotically something like this. It looks like pi squared over the normalised length squared. So you get this kind of amazingly simple formula for the asymptotic change in volume. And there's a similar sort of formula for the change in the core geodesic length. So if you have the core geodesic length is asymptotic to 2 pi over L hat squared. So in particular, okay, so you can see this tells you how fast the volume is converging to this limit point. And this shows that as L hat gets bigger and bigger, the length of the core geodesics are going to 0 in a nice controlled way. Okay. So that's the result of Neumann and Zege from the 1980s. A more recent result kind of refines this. Instead of these kind of asymptotic behaviour, you can actually get upper and lower bounds on these quantities which correspond to this kind of behaviour in the limit. So some work of myself and Steve Kirchhoff actually gives you upper and lower bounds which are similar to this. Okay, so we have this very good control on the change in geometry when we do downfilling. Now you might ask, okay, what happens to all these arithmetic invariants when you do downfilling? And I guess, I don't think, there's not actually a lot known about this. I think there's some good questions here for further investigation. But I just want to mention one result, which I proved a while ago. This is going to say what happens to invariant trace fields, or something about it, as you do downfillings. So if we have a one-cusped hyperbolic three-manifold, and we look at the invariant trace field, let's say KPQ for M, downfilling MPQ, then what we can say is that the degree of this trace field, it goes to infinity as the surgery coefficients go to infinity. Okay, so somehow, the field is getting more and more complicated, the degree is getting bigger and bigger as you do these high-order downfillings. Okay. Now, the proof of this, it's not too difficult, and I think I don't really have time to go into it, but I could explain it to you if you're interested. It's not too difficult to do. Basically, the idea for the proof is to look at the core geodesic in these hyperbolic manifolds and say, look at the eigenvalue of that. What we can see, we're going to then show that the eigenvalue for this core geodesic, it satisfies some minimal polynomial, and we can show that the degree of that minimum polynomial goes to infinity. Once you know that, you can also see that the trace of this group element, that has some minimal polynomial with degree going to infinity, and that forces the degree of the whole trace field, or the whole invariant trace field, to go to infinity. So it's kind of analysing what happens to this core geodesic to prove this result. Okay. But so I think it's an interesting open question here, is to try and get more information about how these kind of algebraic and arithmetic invariants behave when you do downfilling. Okay, so at this stage I'd like to move on to the kind of other part of the talk for today. So we're kind of changing topics at this stage. I want to go back to methods for computing hyperbolic structures, this time on three-dimensional orbifolds. So just a quick reminder. So as you've seen in Professor Choi's lectures, a three-dimensional orbifold is basically a space modelled on R3 modulo finite groups of diffeomorphisms. And in dimension 3, if you have an orientable 3 orbifold, it's completely determined by giving, there's an underlying topological space, which I'll call, say, Q. This will be an orientable 3 manifold. And inside this you have a graph, which is a singular locus, which corresponds to points which are fixed by elements in these finite groups. So if you go upstairs, you have these finite group this finite group. It might have some fixed points for some of the elements. The images of these fixed point sets gives you the singular locus in the orbifold. And I guess again from Professor Choi's lectures, this is actually a trivalent graph. You have 3 edges coming into any vertex. It could be disconnected, could even be empty, in which case you get a manifold. And for each of the edges or circles in this graph, you have an integer, n greater than or equal to 2. So that tells you about the order of the cyclic group corresponding to a point in the edge. Okay, so in fact, so you can describe these things just by drawing pictures. You start by drawing some three manifolds. So here, for instance, we could take the three sphere. We draw some trivalent graph. So here, each of the vertices has got three edges coming in. You can put some labels on all the edges. So a picture like this gives you an example of a three-orbifold. Notice we could have some components which are just circles. And the graph could be disconnected, as in this example. Okay, so such a thing gives you an orbifold. Now, we're interested in hyperbolic structures on this orbifold. And I guess roughly one way to think about it, it's some kind of singular hyperbolic metric where you have cone points along the singular locus. So if you take sort of one of the edges which is labelled n, a cross-section should be a hyperbolic disk with a cone point of 2 pi over n at the centre. Okay, so this is a picture for a hyperbolic structure on one of these orbifolds. And I guess we can actually allow, okay, some sort of general things here. So the typical case, if the sum of the angles at a vertex is bigger than 2 pi, we actually just have a finite vertex, which is the usual case that people would consider. Yeah, so for instance, do I have some in this picture? Let's have a look. Maybe not. So here, for instance, we've got 2, 3, 4. Let me give it a finite vertex. Yeah, that's going to give a finite vertex. If you have the sum of angles at a point equal to 2 pi, what you can do is actually remove that point and you end up with a cusp in your manifold. So, and finally, if you've got a point where the sum of the angles at the vertex is less than 2 pi, what you can do is actually remove a neighbourhood of that vertex, so get a sphere as the boundary, and you can make that into a totally geodesic boundary component, which will have a sphere with a hyperbolic structure and 3 cone points. Okay, so you can probably ignore these last two for today. This is the typical case, but you can allow these kind of more general things as well. So, okay, so how can we compute hyperbolic structures on these things? Well, the idea is the same as usual. We start by decomposing our manifold, or in this case our orbifold, into tetrahedra. Then we want to find shapes for the tetrahedra. So for instance, you need to know the dihedral angles and the edge lengths so that we can glue the faces by isometries. And if we add up the angles around an edge, that should be 2 pi. Or if we've got an orbifold, we might have an angle of the form 2 pi over n that we want along the edge. Now I guess there's a few complications if our space is non-compact. In particular, you need sort of completeness conditions, as we saw yesterday. Now, in fact, there's various kind of generalized tetrahedra we can look at in hyperbolic geometry. And it's useful here for dealing with all the sort of possibilities. So, if we're working in hyperbolic 3 space, okay, usual tetrahedra, a compact tetrahedra with all finite vertices. So all the vertices are inside hyperbolic space. So that's kind of the usual picture, a nice compact tetrahedra. We can also allow ideal vertices. So this is the kind of thing we were using for the figure 8 knot complement. We let the vertices move to the sphere at infinity. But you can even go beyond this. So you can actually let the vertices move outside the sphere at infinity. And I guess to understand this, it's easiest to think about the projective model. So here you start with a unit ball, geodesic segments of straight lines inside the ball. Hyperbolic planes are just parts of Euclidean planes inside the ball. So a convex polyhedron in the projective model, it actually just looks like a Euclidean convex polyhedron. So what can we do? If we start, so here for instance, here's a tetrahedron. We've got 4 vertices. First vertex is a finite vertex. This vertex is it's an ideal vertex, it's on the sphere at infinity. We've also got 2 vertices outside the sphere at infinity. Now in fact, this is actually some sort of non-compact object, but you can truncate it to get something compact. And here's the idea. If you have an hyper-infinite vertex like this, that determines a kind of dual hyperplane. So there's kind of a nice geometric picture which you can see here. You look at a cone with a vertex at V and tangent to this sphere at infinity. Okay, so you have this kind of tangent cone. That meets the boundary of the sphere in a circle, and that circle bounds a hyperbolic plane. So starting with V, you get this kind of V perp, which is a dual hyperbolic plane. And what you can do is truncate along this dual plane. Similarly for this vertex, you get a dual plane like this. If you cut along the vertices, you get some compact object like that. So here we've got a finite vertex, an ideal vertex, and you see 2 little triangles corresponding to the hyper-infinite vertex. So it turns out these things are very useful. So it's useful to work with these generalised tetrahedra for computing and studying hyperbolic structures. Okay. All right. So what I'd like to do now is describe this computer program called ORB, which is written by Damien Hurd. So I'll say a few words about how this works. Okay, so the idea is basic building blocks are these generalised hyperbolic tetrahedra. It can allow all these 3 kinds of vertices, and you can actually pass sort of continuously between different types. You can allow the vertex to go from finite to ideal to hyperinfinite and backwards and forwards. It can also sort of allow tetrahedra to flatten out, even to turn inside out. So this turns out to be useful for doing calculations robustly when you're trying to deform geometric shapes. It can work with orbifolds and also cone manifolds, where you have some cone angle around an edge, but not necessarily 2 pi or 2 pi over n. So you can study all these sort of general kinds of objects. And actually it works, the interface, it's a bit like Snappy. So how can you start? You can start by drawing a projection of a graph. So you take a graph with trivalent vertices, you draw it using the mouse, and then you can try and find hyperbolic structures with prescribed angles or prescribed orders for an orbifold structure around the edges. Okay. So here's kind of a brief outline of how it works. So let's suppose we've got something like an orbifold in the 3-sphere. Singular locus is a graph with integer labels on the edges. And I guess for today, let's just assume that all the vertices are finite to describe how things work. Okay, the first step is to find a suitable triangulation to work with. So given a projection of this graph, first step is to find a triangulation of the whole 3-sphere with sigma contained in the 1 skeleton. And this is actually, it's very similar to what I showed you yesterday for the figure 8 knot complement. You can start by something like finding a spanning 2 complex, look at the complementary regions, and then sort of subdivide it into tetrahedra. So by extending the kind of approach of Thurston and Jeff Weeks in Snappy, you can find such a triangulation. So we've got the 3-sphere triangulated, the graph is made up of some of the edges in the triangulation. Now you can also try and simplify the triangulation by using things like these 2 to 3 and 3 to 2 moves that I showed you yesterday. And I guess the aim is to try and get the triangulation as simple as possible. Okay, so now how do we compute hyperbolic structures? Well, basically we need a way to parameterize the shapes of all the tetrahedra. It's a bit more complicated than for ideal tetrahedra. There we just had a complex parameter describing the shape. One way to do it here is to keep track of something like the edge lengths. And I'll stick to the case of tetrahedra with finite vertices. Turns out to be slightly better to work with coshers of the edge lengths. So these are going to be the sort of basic parameters. And I guess there's a slight variation on this. If you have, say, hyperinfinite vertices, you first truncate all the vertices and you measure the distances between these where you've truncated, so you get finite lengths again. If you have ideal vertices, you can choose a horosphere around each vertex and you measure the lengths between the horospheres. So there's a way to kind of use something like lengths in each case here. So once you know the edge lengths, or coshers of them, you can calculate all the dihedral angles. So you can go from the edge lengths to the angles quite easily. And because if you've got two faces that are going to be glued together, the edge lengths naturally match up. So you can glue the faces together by isometries. Okay. So you can glue things, you can always glue them by isometries. So the only problem is to make sure that the angles add up correctly around the edges. And that gives you some kind of system of nonlinear equations that you need to solve. And again, so orb works numerically using some version of Newton's method to solve these equations. As a starting point, turns out to be good to use some kind of regular generalized tetrahedra as the initial guess. So you start with that and then you try and deform it by using Newton's method. And usually this works very well, so you end up with a numerical solution to these equations. Once you've got this, you can start computing lots of interesting geometric invariants. So again, by Mostow-Prasad rigidity, hyperbolic structure on the orbifold is unique, and geometric invariants are actually topological invariants. So sorts of things you can calculate using orb are hyperbolic volume. So that uses some formulas of Akira Ushijima for calculating volumes of these generalized hyperbolic tetrahedra. You can also come up with explicit matrix generators for the corresponding discrete subgroup of PSL2C. You can do things like find Dirichlet domains, so that gives you a nice picture of the hyperbolic structure. And you can do things like lengths of closed geodesics, find presentations of the fundamental group, you can look at homology groups, and you can look at covering spaces. So I guess most of all these things on the list are things that Snappy will also do if you have, say, a closed manifold or a cusp manifold. But yeah, so orb allows you to extend all these things to general orbifolds. Now, I guess I mentioned in passing last time, for cusp manifolds, there's a kind of canonical triangulation or canonical cell decomposition. And it turns out there's a similar thing here. There's a canonical sort of cell decomposition. In this case, it was defined by Kojima. And that's a complete invariant for the kind of hyperbolic structure. So using this, you can also decide if manifolds are homeomorphic, and you can also compute things like their symmetry groups. Okay. So I guess at this stage I'd like to talk just about a couple of applications of these ideas in this program orb. So So I guess if you're interested in knot theory, this program Snappy has been extremely useful for extending the classification, building up knot tables. So in fact, I guess, yeah, so that played a big role in, say, building the work of, I guess, a bunch of people. I guess there's Jim Hosty, Thistlethwaite, Jeff Weeks and others, built up, say, knot tables up to 16 crossings. I think there's about a million or so knots up to that point. So using hyperbolic geometry, invariants calculated by Snappy, these can all be classified. Now, there's a kind of natural problem if you're thinking about graphs. It's to try and build up a classification of knotted graphs in the three-sphere. So, right. So if we're interested in this sort of situation, we're interested in knotted graphs in S3 up to isotopy. So again, it's an interesting problem to think about. So how can you tabulate and classify these kind of graphs? So but there hasn't been as much work on this. This is much less studied than the knot theory problem. I guess one of the sort of first results in this direction was about 1989. Rick Litherland produced tables of certain kind of theta curves. I'll show you pictures of those in a moment, up to 7 crossings. And he used some sort of polynomial invariants to distinguish the graphs. I want to talk about some work. So it's with Damien Hurd and 3 undergraduate students, James Saunderson, Nick Sheridan, and Maurice Kyodo. We were trying to extend these tables by using invariants coming from hyperbolic geometry. I guess some other work here, I guess, was done by Moriuchi, again using a Yamada polynomial invariant. But what we've done is shown these graphs can all be distinguished by using hyperbolic invariants computed from orb. And in fact, there's actually a nice complete invariant. There's a kind of canonical cell decomposition again, which is important in this case. So let's see. So the idea is, if we're looking at a knot, the idea is to find a complete hyperbolic structure in the knot complement. Here what we want is something which is kind of analogous to a complete hyperbolic structure on the complement of the graph. So let's see. So what should we take? The idea is to look for a hyperbolic structure with geodesic boundary made up of 3 punctured spheres, so that the meridian curves on these spheres are all parabolic. You can think of this, it's kind of a limiting case of orbifolds, where you take all the labels on the edges going to infinity, and you let all the cone angles go to 0. So I'll show you an example of this in a moment, so that'll make this kind of more concrete. But once you've got this thing with geodesic boundary, you can find this Kojima canonical decomposition, and that actually determines the graph completely. Another nice thing you can do here is determine the symmetry groups of these graphs, because any symmetry has to be a symmetry of this canonical cell decomposition, and that's just a combinatorial problem. Okay, so here's an example. Okay, so this is how does this work in maybe the simplest case. So what's a handcuff graph? Well, I guess we know what handcuffs are. You have kind of 2 rings joined together. So on the right we have kind of a knotted pair of handcuffs. So here's one circle, another circle joined by an edge. Okay, and this is kind of the simplest picture of our kind of knotted handcuff graph. Now, in fact, it's not hard to triangulate the 3-sphere with one tetrahedron so that we end up with this graph in the 1 skeleton. So here's the picture. So you start with a single tetrahedron. You take the 2 front faces, so they take the 2 triangles on the front, and you fold them together. Okay, so the top part gets folded to the bottom. And so this blue edge gets glued to this edge gets glued to this. So that's the first step. You fold the front together. Next, you take the two back triangles and you fold them together. So you fold that at the back. And if you think about this a bit, you can convince yourself this gives you the three-sphere. And inside the three-sphere, you can see the one skeleton's made up of this. You get a red circle corresponding to this red edge. You get a green circle corresponding to this green edge. And the four blue edges fit together to give you this blue edge in the picture. Okay, so that's a good exercise to check this identification, gives you this picture. Okay, so this is kind of as simple as you can get. We've just got one tetrahedron glued up to give the three-sphere and this graph. Now, I want hyperbolic structure with parabolic meridians. So the way we're going to get this is start by looking at truncating the tetrahedron. And so I'll show you the picture, I think is... Okay, so here's the picture. So start off... Okay, so here's our original tetrahedron. We cut off the corners. So we remove these little triangles. Now imagine truncating more and more so that the lengths of the edges go to 0. So you kind of take bigger and bigger triangles here, let the edge lengths go down to 0, and there's kind of a limiting picture, which is this one up shown in the top. So we have, again, 4 triangles, but now they just meet at sort of points in the middle of the edges. Now, in fact, this is going to give us exactly what we want. So if you just look at the part, so we've removed all the outside here. What's left, it actually turns out to be an octahedron, as you can kind of see in this picture if you look at it closely. And we've actually got, it's actually, and yeah, so what we're going to do now is replace it by a regular hyperbolic octahedron with all ideal vertices. So we take all of these points at infinity, you take a nice regular octahedron, and then everything fits together nicely so the angles will all work out correctly, and we end up with a hyperbolic structure on this link complement. Okay, so some of the faces get glued together in pairs. The other ones form two totally geodesic three-punctured spheres, and that's, you get these kind of orangey faces fit together to give you one boundary three-sphere. The two green triangles fit together to give you a second three-punctured sphere. So that these are going to be totally geodesic. And that gives you one of these special hyperbolic structures. So it's like taking the complete structure on a knot complement. This is kind of a complete hyperbolic structure on the graph complement. And it turns out, so this thing is unique. So if such a thing is unique, if it exists, you can some version of Mostow rigidity by using some kind of doubling argument. You double along the totally geodesic boundary. Now, in fact, okay, this is a particularly nice example. Turns out that it has the smallest possible hyperbolic volume for any kind of trivalent graph. And that was proved in the work of Miyamoto and Kojima. So it's known, this example I showed you actually is the smallest volume sort of hyperbolic graph. Okay. Okay. So if we go, now if we use this to try and classify these knotted graphs, well, the first things that we kind of really studied were these theta curves. So you take a theta graph. So in other words, so that's something with two vertices joined up by three edges, as in this usual theta. And there's all sorts of knotted versions of this. So Lithlin started building up tables. Okay, the first ones on his list are shown here. First one's just a trefoil knot together with an extra edge. The next one, I guess, is a figure 8 knot with an extra edge. And here's the next couple on the list. If we use orb, we can compute invariants for these hyperbolic structures. So for instance, for the first one, we get a volume of 5.333 approximately. Next one's volume about 7.7. Next one 10.39. Next one 8.92. And in fact, by using these hyperbolic invariants, we could completely distinguish all the things in Litherland's lists. We also get some extra information about symmetries. So for instance, this first one has a symmetry group D2. That's a dihedral group with 4 elements. This is also D2. This has a symmetry group D3, and so on. Okay. Okay, so the other thing we did was try to extend these kind of tables of knotted graphs. So in this kind of project with these undergraduate students, we were looking for prime knotted trivalent graphs in the 3-sphere with just 2 or 4 trivalent vertices. And we restricted the number of crossings to get some reasonable list. Okay. So just as in knot theory, you can kind of simplify this classification procedure by working with prime graphs. So a prime graph is one that can't be simplified by sort of cutting along a sphere, meeting the graph in 2 or 3 points. So you see on the left-hand side here, if you cut along this kind of dotted sphere, you can cut it open and you can simplify the graph into 2 simpler pieces. Similarly, on the right-hand side, if you've got a sphere meeting the graph in 3 points, you can cut it, divide the graph into 2 simpler graphs. So it's actually enough to work with these kind of prime graphs. So what we did here, it's based on Conway's approach to tabulating knots. So, okay, first step is to actually tabulate some kind of polyhedra with vertices of degree 3 and 4. I'll show you a picture of that in a second. And this is basically a problem in sort of enumerating planar graphs. In fact, there's a very nice program called Planetary, written by Mackay and Brinkman, which is very good at doing this kind of thing. So we made use of this. So here's a few typical examples of these sort of polyhedra. Okay, so the one in the middle, okay, it's got 4 trivalent vertices at the outside. And I guess you should imagine the thing in the middle, that's supposed to be a kind of big degree 4 vertex. Okay, so imagine that's a single big point in the middle. So here again, there's some trivalent vertices and have these degree 4 vertices. So there's a few simple pictures. The ones we look at are ones that basically can't be divided into simpler pieces by cutting along circles, meeting the graph in a few points. Okay. So now if you have something like that, now we want to remove a little neighbourhood of these 4 valent vertices. So you enlarge it to get sort of a circle, as in this picture. And then you want to fill in so-called algebraic tangle in each of those little circles. So this is basically Conway's procedure. I won't say exactly what algebraic tangles are, but they're sort of special kinds of, well, a tangle consists of 2 arcs sitting inside a 3-dimensional ball. The algebraic ones are particularly nice. Basically, you can kind of untangle them by twisting along the boundary components. Okay, so there's a whole nice way of building up these algebraic tangles, which was worked out by Conway. So for each of the pictures up the top, you start filling in all these different sorts of tangles, and that gives you all the possible projections up to some number of crossings. Okay, so that's the first step. Start enumerating these projections. Now at this stage, there's probably lots of repetition. First of all, you might have different copies of the same projection. So first thing is to get rid of repeated projections. And there's a nice way to do that by using this kind of a canonical description of these projections, which uses the ideas of planetary. So first you get rid of repeated projections. But now we want to know whether these projections really correspond to the same graph or different graphs. And here we need some invariants. So this is where we use hyperbolic geometry, and we look at hyperbolic invariants computed using orb. So I guess the two main things we looked at were volumes. So there's hyperbolic volumes, for instance, of associated orbifolds. And the other thing which we can use is Kojima's canonical decomposition. So using this, you find lots of projections actually give you the same knotted graph, but we can come down, we can decide which ones are equivalent, and we come up with a complete list of these sorts of graphs. Okay. One other kind of work in this direction was some work with Damien Hurd, Bruno Martelli and Carlo Petronio. This did something similar, but this was working with knotted graphs in general three manifolds, not just in the three sphere. Okay. So let me just show you now a few results, sort of results we're getting. So if we look at the graphs in the three sphere, it's up to 4 vertices and 7 crossings. Actually already lots of them. Now, on the left, these are the various kinds of underlying sort of abstract graph that come up. The first one's a theta and so on. Okay, so there's quite a lot of these different sorts of things coming up, even up to just 7 crossings. We weren't necessarily restricting to connected graphs. So you can also have these kind of basic graphs on the left together with extra circle components. So you could have extra knots as well. So the second column, for instance, says we end up with 143 graphs made up of this kind of trivalent graph plus some knot as well. And there's a few with 2 sort of knotted components. Okay, so there's lots of these things, and to classify them we really needed some good invariants, so that's where the hyperbolic geometry came in. The other thing I wanted to mention is, okay, remember that a 3-dimensional orbifold is described by giving some sort of trivalent graph together with labels on all the edges. So if we start with one of these knotted graphs, you can start generating hyperbolic orbifolds. Oops. Ooh, okay. Maybe I should plug this in just a second. Okay, we'll have a slight pause here. Oh. Get some more energy to continue. Okay. Okay. Okay, so now, so what can we do? Well, the idea is just to start with these knotted graphs, so they're trivalent graphs. You can start assigning numbers to all the edges. That gives you orbifolds. And then we want to try and look at which ones have hyperbolic structures. So again, you can try and do this using orb. So I'm just going to show you a few of the kind of interesting things that come at the start of the list. So I guess in this picture, okay, so here's some of the beginning. What we've got, so here's some sort of graph. We've got this edge, for instance, is labelled 3, this edge is labelled 5. All the other edges are labelled 2. So if there's no label, that means 2. So here are the lowest volume ones that come up. So the first one has volume 0.03905. And it's actually now known, it's been proved quite recently by Martin and Marshall, that this is really the lowest volume, I guess, for say closed orientable 3 orbifolds, hyperbolic 3 orbifolds. The next volume we came up with was this one, 0.04089. So here there's 2 edges labelled 3, all the other edges are labelled 2. And that's also known by this work, that's the second lowest volume for these orientable hyperbolic orbifolds. Okay, the next one, okay, so here's the next one on our list, is volume 0.05. And this one was volume 0.659. It turns out all of these lowest volume ones are actually arithmetic. And in fact, the first, I'm not sure, at least the first half a dozen or more on the list, they all turn out to be arithmetic. I'll show you, here's a few more. I guess here's the next 2 on the list. One interesting feature is all the lowest volume ones actually have 4 vertices. They all have 4 trivalent vertices. If you go to 2 trivalent vertices, this one on the picture is the smallest volume that we've found. That's a bit bigger, 0.117 is the volume. We can also look at sort of cusp orbifolds and non-compact orbifolds, and they're the first one we came up with was this, 0.08457. And that was already known by work of Meyerhoff to be the smallest cusped, orientable cusped hyperbolic orbifold. Okay, so at least, so for this kind of enumeration we're doing, we do seem to be coming up with the lowest ones on the list. But at this stage, I guess only the first 2 have been proved to be the lowest volume. Okay. Anyway, so there's some other interesting orbifolds. And these are related to some of the arithmetic groups that Alan was looking at yesterday. So I thought, let's see, thought I'd finish up today just with a few sort of open problems. So from the sort of things that we were talking about, okay, one obvious problem is to try and extend the current results to give lists of low volume hyperbolic manifolds and orbifolds of various types. Okay, so at this stage, okay, the lowest volume manifolds of some interesting types have been identified, but we don't know sort of many of, there's only a very few at the start of the list that are actually proved to be lowest volume. So for instance, if we look at closed orientable manifolds, we now know that the Weeks manifold is the lowest volume, but I guess we still don't know what the second lowest volume is, or it hasn't been proved rigorously. We have nice lists of conjectures for these things, but it would be very nice to extend this list, so maybe we get the first 10 or 20 low volume manifolds. Okay, similarly for the closed orientable orbifolds, we now know the first 2 on the list. Again, it would be very nice to extend these lists and go much further. Maybe the first 10 or more on these lists. And I guess, okay. So for both of these questions, you could try and sort of extend the work that's been done so far and refine it to get further in these lists. I guess from this work on things like knotted graph complements suggests another interesting class of examples to look at manifolds with totally geodesic boundary. Again, okay, there's various kinds you could look at here. Compact manifolds with geodesic boundary. The lowest volume example is known by work of Kojima. You can also look at these sort of manifolds with finite volume totally geodesic boundary, which is what we're looking at for these graph complements. And the lowest one is also known for that. But it seems another good problem is to try and extend these lists. Okay. Now I think for a lot of these problems, this work of Gabay, Meyerhoff and Milley, using this kind of MUM technology and rigorous computation techniques, it should be very useful. And it's seems really likely that a lot of these results can be extended by developing these techniques further. And one final question, okay, very interesting question. What happens for non-orientable manifolds? Here, there's much less known. Whoops, yeah, that's supposed to be non-orientable, but anyway, you can. There's a conjecture for the lowest volume. It's actually much bigger than the lowest volume for closed orientable manifolds. Okay, the Weeks manifold was volume about 0.94. Here, I guess, I forget. I think the volume, conjectured volume, is actually the same as the figure 8 nut complement. I think it's about 2.029. I may be wrong, but I think that's, so it's actually much bigger than for orientable manifolds. And I guess very little has been done here. I guess Peter Milley, has some results for these non-orientable manifolds, but the bounds seem to be much worse. So that's kind of another interesting problem where not much has actually been done. And somehow, so it's quite surprising that the non-orientable manifolds seem to be much bigger. I guess one reason, perhaps, is that these always have incompressible surfaces in, so that perhaps forces the volume up. Okay. And I guess, there's lots of other classes of manifolds you could look at here. There's a very nice survey article by Gabay, Meyerhoff and Milley that you might like to have a look at if you're interested in these sort of questions. Okay. Another kind of question, computational question I think is interesting, is to try and extend the capabilities of ORB. For instance, we'd like to have a version which finds exact hyperbolic structures and arithmetic invariants. So SNAP, this program SNAP, does these things for closed manifolds and cusp manifolds, but we don't really have a good way of doing this for orbifolds. There is a way you can actually try to do this kind of thing using SNAP. So what you can do is start, if you've got a hyperbolic structure on an orbifold, you get an approximate representation of the fundamental group. You get a kind of numerical approximation to representation into PSL2C. Okay. So you can try and use the same idea behind SNAP. So, so this representation, it's defined by some generators satisfying a set of polynomial equations which come from the relations. You can try and, first of all, find a more accurate approximation to this representation by using Newton's method to solve these polynomial equations. So that would give you a high precision version of the representation. You might work to 100 or 200 decimal places. And then we know that traces, for instance, of the matrix entries, or I guess the matrix entries themselves, if you normalise things suitably, are actually algebraic numbers. But let's have a look at the traces. Given these kind of numerical approximations, you can try and guess the exact descriptions as algebraic numbers. You try and guess the minimal polynomials by using LLL algorithm, so as SNAP does. And I guess, so you can actually go through this procedure and start, once you've got traces, then you can compute the invariant trace field and the invariant quaternion algebra. So you can kind of do this thing at the moment, but it's not automated, and there's probably better ways of trying to do this. So I think that's another kind of interesting problem. Okay. So let's see. This stage, let's see, I might just go back. So a few references for the sorts of things I'm talking about today. First of all, I guess the original reference is Thurston's Princeton University notes. There's also this very nice paper of Neumann and Zagier looking at volumes of hyperbolic three manifolds. That talks about sort of using ideal triangulations and also these kind of asymptotic formulas for the behaviour during Downfilling. famous article of Neumann and Reed. It's very good for basic information about arithmetic invariants for hyperbolic manifolds. I guess there's also the book by McLaughlin and Reed. It's another good reference for that. For more about this Gabay, Meyerhoff and Milley work, they have this nice survey article, which you can find on the archive. And finally, I guess, if you're interested in this program orb, you can find it here. I think there's a tilde missing. That's supposed to be tilde snap. There's a missing symbol there. But, and there's also this paper which talks about looking at knotted graphs in closed three manifolds, which you might have a look at. Okay. So I think I'll stop there for today. So yeah, thank you everyone, and good, great.
Do you have a question for
Questions? Good.
What is a condition for a graph to have a hyperbolic structure as complement?
Okay. Good question. I probably am going to forget the conditions, so maybe I'll tell you later. Yeah. I mean, roughly, the complement has to be atoroidal and acylindrical. But you have to be a little bit careful if you want these structures with parabolics along the meridians. So, okay, so maybe I can tell you later. I'll check it out.